Well, and actually you may wonder about the title, because this workshop here is about quantum simulation, and I'm talking about quantum metrology. Well, in principle, I did lots of stuff on quantum simulation as well, but this was in the early days of this business, and I think this is more than 5 or even 10 years old, this thing, so I didn't want to talk about this. But on the other hand, I quite recently did lots of stuff on quantum metrology, and as you will see during this talk, these techniques and methods which are developed in quantum metrology, I believe that they can be very useful in this business of quantum simulation as well, because the goal and the setting is very similar. And that's why I'm talking about this kind of results and hope that you will get at least some inspiration or some ideas of how to use all these nice methods people have developed in quantum metrology also in your business. So, but first of all, why quantum metrology? So metrology is about measuring quantities with as high precision as possible, and actually that's our very business. That's what physics is about usually. That you try to well, I would say it's a problem of utmost importance in physics, but also beyond. It's also in other sciences that you would like to investigate something, you would like to measure things, and see how things behave and see what number or how this constant looks like. And for this, it would be good to have methods to do this with as high precision as possible. And actually, it was realized, I would say 15, 20 years ago, that actually quantum mechanics allows an advantage there. Namely, if you compare the best thing you can do classically with separable probes, with what you can do quantum mechanically when you allow for entangled input states and when you allow for joint measurements on your probe system, then people have realized that actually you can get a quadratic improvement by using this quantum toolbox, by using this quantum features. And I would say entanglement is a key issue there. So this sounds very nice. So quadratic means it's either a quadratic gain in the time you have available to do the measurement, or it's either a quadratic gain in the number of probe systems you are using. So just think of a couple of spins and you want to measure a magnetic field. You know it's orientated in Z direction, but you don't know the strength. Now if you prepare one of the spins in the plus direction, it starts to oscillate. And if you just have one spin, it oscillates a bit, and then if you do a measurement, and from the strength of the oscillation, so how far it oscillated, you can determine backwards the value of the field. And actually, if you have n of these probes, well, you would just let n of them evolve and then measure them. And from there, there's a certain fluctuations when you do the measurements quantum mechanically, and from there you can deduce the number, the strength of the field. I will show you shortly how you would do this quantum mechanically and why you get this quadratic speedup. But on the other hand, one readily realized that while this quadratic gain sounds all very nice, but once you go in a realistic setting where you include some kinds of fluctuations, some kinds of noise, say you have some dephasing going on while you let your spin evolve, then in this case, all of a sudden this quadratic speedup disappears. And this was first only an observation for some special cases, but then people started showing this more and more rigorously. And also some of the results I'm going to show you today also tell you, well, okay, actually in general, in generic cases, you don't get this quadratic speedup. But still one could ask, are there some situations where you can avoid this influence of noise, or so you can go around? Because we all know that in quantum computation there are these powerful techniques of quantum error correction. You are aware of this fast control, and can you use all this to avoid, or at least to get rid of some of this noise? And on the other hand, the scaling advantage is very nice, but in many cases one would be happy enough just to get a constant vector if this vector is huge or large. So if, say, think of the LIGO experiment, so people are very struggling there to get one order of magnitude advantage, and in fact, they have started to using these quantum effects there, but not for a scaling advantage, but just for a constant factor. So they are happy enough about a factor of 3 or say 10. So even though there are no-go results for a scaling advantage, it could still be, and I will show you that it is in fact the case, that in many interesting situations, you can still get a huge improvement using these quantum resources. So, and I already told you why I think this is relevant for quantum simulation as well, because in quantum metrology, you have a Hamiltonian which evolves, and there you want to measure some quantity of this Hamiltonian, say the strength of a field. And on the other hand, you have this nasty noise, and this nasty noise, whether it comes in additional terms in your Hamiltonian or whether it comes because of some additional terms in a master equation, you want to get rid of them, or at least of some of them, or you want to study the influence of them. And that's actually very similar to what you do in quantum simulation. There you also have some sort of target Hamiltonian, some evolution you want to induce in your system. Maybe you want to manipulate it as well. That's what happens in this digital simulation, that you not only sort of let the system evolve with your magnetic field, but you want to control things a bit and mimic other evolutions. But at the same time, still you will have some noise effects, and still you would like to get rid of these noise effects, or at least to study what's the influence of them. So that's why I think these techniques and methods I'm going to present you could be useful or will be useful in the quantum simulation business as well. So, well, I will talk about 3 different things. The first is really ultimate limits on quantum metrology. So what happens if you are equipped with the full power you can imagine? What are the limits? What can you do? Is there a scaling advantage? When is there a scaling advantage? And how could you get it? And when there is no way around. The second thing is about the more specific. It's about using quantum error correction. Because the first, I believe that coming from this quantum computation side, where all the errors can be corrected, I believe that, well, this should happen in quantum metrology as well. We have these powerful methods of controlling errors, but it's a bit more tricky here, because in quantum computation, you know exactly what happens or what should happen. In many cases, it should just happen, nothing should happen, and you want to protect things. Or a specific gate should happen, and you want exactly this gate should happen. But in metrology, you don't know exactly what's going on. So there is a field, you know things are rotating, but you don't know with which strength. And this actually makes this business a bit more tricky, and in some cases you can still control and still correct for errors, but in some cases you can't. And the last thing, and this is about very recent stuff, it's about non-local sensing, where you are no longer interested in some local quantities, but you think more of a global scale, where you are interested in, say, distributed sensors. You can think of a sensor network arranged all over the Earth, and then you want to measure some non-local quantities, like this telescopic arrays. But this non-local sensing can also be in a smaller scale, say within a trap, in an ion trap, where you have particles arranged on different positions, and you were interested in a non-local quantity like the gradient. And still you would like to measure this with as high precision as possible. And I will tell you a little bit of what additionally you can do in such a setting, and actually you can do much more than in a local sensing scenario. But let me start with metrology and a little bit of a background. Well, in parameter estimation, what we do is you have an evolution with respect to some operator A. So you can think of a Hamiltonian, this local field, with some parameter theta, and you want to learn this theta. And for this, you prepare some probe systems, you let them evolve, and then you devise the most clever measurement which comes to your mind. And then from there, from your measurement data, you make predictions with an estimator about the value of theta. And the Grama-Rao inequality tells you that actually the accuracy, with which you can determine the theta, is given on the one hand by the number of repetitions of the experiment, this is the small n, and on the other hand by the quantum Fisher information. And the quantum Fisher information is a quantity which which depends on the initial state you prepare the system in and on the operator you want to measure. Actually, for For pure states, this quantum Fisher information is nothing else than the variance with respect to this Hamiltonian your system evolves. Okay? So this is just the variance of your system with respect to this Hamiltonian. And you can easily imagine if the variance is big, sort of your system evolves a lot, and it's easy to distinguish them. That's sort of the idea you can have in the back of your mind. And actually this Fisher information, that's a metric in the space of density operators. So you take a density operator, you take a second one, which is parameterized by this time evolution, and then you look at two different points, and then you are interested in the distance between these 2 points. So just think of your evolution. So this your magnetic field lets your spin rotate, and the farther you get away from your initial point, the better distinguishable these two resulting states are. And this is exactly what this Fisher information measures. It's really just the distance between these two points in your space of density operators. And actually it turns out that the quantum Fisher information that's of order n, so big N is the number of probes for all sort of classical systems or for all separable or product states. And on the other hand, the Fisher information is quadratic for something like Greenberger-Horn-Seilinger states. Yeah. Microscope, okay, I could talk more about what is meant there. There are approaches to this macroscopicity where the Fisher information serves as a measure, and microscopically entangled, what I mean is that only a small number of particles are actually entangled, and not sort of the whole system, as is the case for a GHZ state. So microscopically entangled, I would think of a collection of Cooper pairs, say, where you only have sort of a collection of entangled pairs, only two particles being entangled, and no, well, if you have k particle entanglement, actually you can get a factor of k. But if you have only Bell pairs, then it's just a factor of 2. You don't get the scaling. That's what I mean. So in order to get the scaling, you go to this quadratic. It scales in the number of particles which are entangled. Yeah. Okay. Now, if you use a GHZ state for sensing, and I'm still with this example with this local magnetic field, well, actually, each of these spins gets a phase vector, and now since all of them are in the state 1, and each of them gets a phase, so this phase is sort of amplified by a factor n. So it's not so this big spin, so this GHZ state you can sort of think of as a big spin in a big Hilbert space, and this now rotates much faster, namely by a factor of n faster than an individual spin. And this is what makes the sort of the accuracy of your metrology protocol quadratically better. Okay, but on the other hand, if you have some sort of dephasing noise, so if you have some noise happening, so this is a depolarizing channel, on top of it, it's also dephasing channel would be sufficient. Now, sort of the key thing, what makes up the quantum advantage are these off-diagonal elements, if you write it down in your density matrix. But these off-diagonal elements, due to this noise, which acts on each of the individual qubits, this is exponentially damped. That's what happens. That's also something we sort of know, that if you have a bigger system, a highly largely entangled system, typically the entanglement or the coherences in these systems disappear, and they disappear much faster if the system is large. And that's exactly what you can see for this GHZ state. And this is also what makes the quantum advantage disappear, because your signal is damped by this exponential factor. So in this sense, the quantum Fisher information is then again limited to n, which means that, well, no quantum advantage. Okay, but I promised you to tell you something about ultimate limits in metrology, and namely using full quantum control. So the time when we started this business, there were already some sort of powerful no-go results there, saying that if you prepare your system, let it evolve, you have some noisy evolution, and do a measurement at the end, actually, whenever you have a full-rank noise process, so a generic noise process, there is no quantum advantage. But then we said, well, that's not all what you can do. You shouldn't only wait until the end of your process, but in principle, we could also interfere at intermediate stages. So we could try to use some encoding, do some error correction, and we could try to make corrections at very small time intervals. And that's actually the scenario we were considering. But then there are sort of two different ways how you can describe your noise. There is sort of the generic way when you use a master equation. And there is also sort of the scenario or the situation where your control operations are really, really fast and things happen at time scales which are shorter than the time scales such that your system environment interaction takes place. And actually, in this limit, you can describe everything still with a Hamiltonian picture. You don't need to go to a master equation, you don't need Liouvilleans. If you really have ultra-fast control, your time scale you can control your system is faster than the system environment interaction, the relaxation time which you get there. Then everything is Hamiltonian. That's the first scenario to look at. And, but then there's also the scenario, and that's the second thing I'm going to show you later, is when your time scale is still fast, you can still have fast control, but it's not faster than a relaxation time. So you're not allowed to write down Hamiltonians anymore, so you have to describe your system environment interaction not by a Hamiltonian, but by some master equation, by some Lagrangian. And actually these two scenarios turn out to be a bit different. Namely, in the Hamiltonian scenario, you can do a bit more. And let me start with this. So the idea is that you have your Hamiltonian, your system evolves, and then you can interlace this evolution with fast control operations. And I guess most of you have heard about this dynamical decoupling, that you sort of let your system evolve for a bit, you change your spin vector, you let it flip, and then sort of the evolution goes backwards then due to this flip for the next time interval. So actually you're evolving backwards, evolving backwards. And by this bang-bang control, by sort of changing this direction of your evolution, so for this Z rotation, it would be some rotation around the x-axis in order to change the sign of your Z Hamiltonian. And if you do this fast enough, you can go to the first order Taylor expansion in your time evolution. And in this way you can cancel. But by doing more clever operations, you can do this dynamical control. You can do this digital quantum simulation. So, and in fact, what it turns out here is by this fast control, you can get rid of lots of noise, namely all the noise which is of rank 2. Only the noise which is parallel in the direction of your evolution, you cannot cancel this. Well, somehow that sounds natural because, well, if you have an evolution with respect to the rotation around the z-axis and you know that you have an additional field which fluctuates around the z-axis, well, this additional field which fluctuates will wash out the information of your vector and will wash out sort of the value of your parameter. So you cannot expect to get rid of this kind of noise. But if you have orthogonal noise, so not noise in z direction, but in x or y direction, this you can get rid of. But it's a bit more than this, actually. Well, so in general, still we are in this scenario, you want to sense the field, strength of a B field in z direction, you have additional terms in your Hamiltonian, say in x and y direction, and then you let the system evolve, do something in between, let it evolve, and since you can choose operations here and here, you can sort of manipulate your Hamiltonian, and since you can do things in a trotterized way, it's like that you
that the effective Hamiltonian you get is just the sum of all these individual Hamiltonians, and this allows you to erase things. Now, so this is for the single qubit, still the same setting. Now the decoupling strategy is exactly to modify these Hamiltonians. Well, if you have start with the simplest case. If you have just X noise, if you have an additional Hamiltonian which goes in X direction. Now, I told you before, in order to sort of undo or change the sign of this Hamiltonian of the X, you need to do a rotation around the Z. Well, this rotation around the Z doesn't change your Z evolution, it commutes with it. So nothing happens to your Z evolution, but your X evolution gets a negative sign. So in this way, you can really just cancel the X. And in the very same way, you can also cancel the Y, because the same sort of Z rotation, which changes the sign of the X, also changes the sign of the Y operator. And in this way, you get rid of the X and the Y. So that's quite easy to understand how you can get rid of X and Y noise, but actually you can do more. Namely, you can, if you have not X and Y, but some sort of noise which is not completely perpendicular to your evolution, but sort of is very close to the Z rotation, in fact. So you can think in terms of the Bloch sphere that your signal is in the Z direction, but your noise is somehow in a tilted plane, something like this. Now, what you can still do is actually to get rid completely of this whole noise in this perpendicular plane by choosing now sort of your vector where you flip around perpendicular to your plane. So you get rid of all this noise, but since you choose it perpendicular to this, also some part of your desired evolution cancels out. Namely, the one which is not orthogonal to, or the one which lies in this noise plane. The rest still remains. Well, actually, that's not really a problem, because the only thing what happens is sort of the strengths of your evolution. You can really think in terms of geometrical vectors there. They just get projected. It just gets a little bit smaller, but still it's there. And the only thing what you want to achieve at the end is to learn the strengths of this field. And now, so sort of you want to learn the length of this vector, but now you have projected it down a little bit, but you know exactly how you projected it down. You just shrink your vector by a constant factor. But this constant factor doesn't hurt you for the overall scaling, because the scaling is still quadratic. So this smaller length is sort of a constant reduction in your gain, a constant reduction in your accuracy, but this quadratic scaling advantage is still there. So actually with this method, you can really get rid of all rank 2 noise as long as it's not completely in the same direction as your signal. Yeah?
But this would require that I totally know my noise.
Well, you know the direction of your noise, but you don't know the fluctuations.
Okay, but and this is easy to know, or do I have to do a
Well,
noise metrology?
in principle, you can do. In principle, you can do a sort of a channel tomography. But you don't need to know everything, you don't need to know the strengths, but you just need to know the direction. And I would say in many situations you know exactly what you can expect, which kind of noise you would expect in your system, and then you try to go for this kind of noise and get rid of it.
So in a many body system, how would this change then? Would then this direction become like a multi-dimensional vector, or what is this? Somehow it feels a bit like free lunch for many body system, that we can somehow...
Well, for D-level systems, we actually haven't thought about this. But I would expect something similar to happen, because it's really just about sort of being able to cancel some terms, and all these results for this universal Hamiltonian simulation, they also were shown then for D-level systems. So I would say this technique should be applicable as well. Well, what I'm assuming, and maybe I haven't stressed this enough, is that we have individual coupling of your system to your path.
Yes, yes.
That's what, it's not some sort of correlated noise,
Yes.
it's really individual coupling.
Yeah, but it's like the mechanical zine. So you have you see the body in some subspace, and if it's uncoupling with some part of side in space, you always project back the mechanical
Yeah.
So this is exactly
Yeah.
what the dynamic is a different way to. So you can always apply in principle. So you can move freely from the subspace by just projecting. Of course, you need to know the time scales for
Yes.
these projections.
Yeah, sure.
And then you can calculate them in some way, or you won't talk about this.
I won't talk about this. So. I would just say I have this ultra-fast control, and I'm fast enough. I know there are many nasty details you have to. It's a whole business in itself, I would say. Okay, but full rank noise, so rank 3 noise, so whenever you have sort of a component which is completely parallel to your Hamiltonian you want to sense, then you can do nothing about it. Well, nothing, well, not quite. If you have individual couplings and you have some sort of correlated noise, say you have each of the spins is, n spins, each of the spins is coupling to an individual environment, and you have a certain Gaussian distribution for the strengths of this coupling. Now, on the one hand, of course, you can do what you did for the single spin already, get rid of x and y noise, or actually of everything orthogonal. But for this parallel noise, what you can do also is to swap your systems. And actually, if you swap things around, then you symmetrize the effect of noise. So actually, when you think of this big noise as a noise of the whole system, there's a symmetric part and an asymmetric part. And by switching things around, this doesn't change the signal because your signal is symmetric. Every spin sees the same constant field. So the signal is unchanged by this swapping. But by doing this swapping, you get rid of this antisymmetric part of the noise. Only the symmetric part remains. And actually, with this example of some Gaussian width of the strengths of these couplings, you get again some Gaussian for your symmetric noise, but the width of this Gaussian is smaller than the width of the individual ones due to this swapping. So some of these sort of different strengths which you get, they cancel out, and you get something which fluctuates a bit less than the individual ones. And actually, this allows you, and I won't go into details, to get not really the Heisenberg scaling, not this quadratic scaling in this case, but to get a scaling which is larger than n, but it's smaller than n squared. So it's n to the 3 halves, what you get there for your quantum Fisher information, and at the end for your accuracy. So actually, even if the noise is parallel, you can do something. In this case, it's a very complicated thing because you have n spins and you have to swap them around randomly and continuously. But at least there's a way to fight this influence even of parallel noise. Okay, but now let me switch to the more general setting, namely the setting which is described by a master equation. And the scenario I have in mind there is now really that you have, for your metrology protocol, you have a full quantum computer available. You can do encodings at the beginning, you can do arbitrary operations on your probe system, prepare them, you let them evolve for a very short time, some dt, and then you can again do everything. You have the full power available. You can prepare new states, you can have ancillas, you can manipulate your system at each individual time step. So that's really the full power you can imagine. And now under this setting, what are the limitations there? And actually what one finds is that for generic noise processes, namely rank 2 noise or rank 3 noise, and I'm still talking about qubits, so rank 1 noise would be just a Pauli channel. So some depolarizing channel, or in your Liouvillean some term which includes some sort of a non-coherent term, which is an X, which is a Pauli X. So that's a rank 1 channel. Now if you have X and Y, this would be a rank 2 channel. And if you have X, Y, and Z as noise operators, then this would be a rank 3 channel. examples of them, of course, only. Now, what turns out is that whenever you have rank 2 or rank 3 channels, you cannot do anything. There is, even with this ultimate control, even with this fast control, even with error correction, you can show that your quantum Fisher information is bounded by n. There's nothing you can do. Only rank 1 noise you can correct. Or only for rank 1 noise, these bounds don't appear, don't occur, but actually you can do more. In this case, for rank 1 noise, you can correct, and you can really achieve this quadratic scaling, this Heisenberg scaling. Okay, I'm not sure how much I should go into detail with this, so maybe just very briefly. So you describe things now in terms of a master equation. You have your Liouvillean, which you write here as a matrix, and the rank of this matrix is really telling you sort of the kind of the noise. And then what you're using is a channel extension method where you can sort of bound the quantum Fisher information just by the Krauss operators and the derivatives of the Krauss operators which describe your channel. Now, in general, when people have started to use this, if you go to larger times, actually you have to solve the master equation and determine the resulting completely positive map. And then from this map, you have to deduce the Krauss operators, and then you can bound the channel. So that's a pretty complicated business. Now, we are in a scenario where we allow ourselves to have this fast control. And actually, that's not only sort of going to the ultimate limits, it's also actually simplifying the problem we have to solve, because we don't have to solve the master equation. We are just in this small dt limit, so we can work in the using the Taylor expansion, or sort of a Taylor expansion of this master equation. And so we don't really have to find the resulting CP maps. We can work on the level of this Liouvillean, and from the properties of this Liouvillean, we can tell when we are able to correct things and when not. Because this channel extension bounds, what you find there is you get you can bound the quantum Fisher information by a term which involves these Krauss operators, which contains the derivatives of these Krauss operators. So, and you can sort of split it up into two parts. One part which is linear in n, and one part which is quadratic in n. Okay? And now you have the freedom to manipulate things. So, or you can also say when you choose your Krauss decomposition, there's a unitary freedom for all these operators. And this unitary freedom, you can make use of it. You can also think of your manipulating things with your fast control. And then it's just a question, by doing this manipulation or by using this unitary freedom, can you make this term here disappear? Because if yes, if you can find operations which allow you to make this term disappear, this means that your Fisher information cannot scale quadratically, because this thing you can make to 0 by doing these manipulations, and this part is the only thing which remains. Okay, so it's just a matter of investigating these matrices which describe your Liouvillean, finding some rotations, some choice of operators, such that you can make these terms disappear. And whenever this is possible, you know that there is no quadratic scaling, there is no quantum advantage to be had. And this actually is the case whenever whenever you have a rank 2 or a rank 3 channel. And I won't go into the details. If you're interested, it's a beast of a 20-page paper. I think it was in the first issue of Quantum. But here you can find, there you can find all these derivations. Actually, for many channels, you can compute this factor, actually this alpha, that's the factor in terms of the linear thing. You can calculate this explicitly, because this alpha can still give you sort of a constant factor, a constant improvement, but not a quadratic one. And only for the rank 1 channels, only for orthogonal rank 1 channels, you can actually, these bounds don't apply, and you can actually still get the quadratic scaling. But the question is, even in this case, even if you don't have a quadratic scaling advantage, what's the factor? Because in some cases you would be happy enough to have a constant factor improvement. And actually there, what we looked at was a very limited scenario, but practically important for experimentalists, namely not working with a huge probe system, which is in a huge entangled state, but just having one probe system and one ancilla system, but manipulate this pair of systems continuously. And compare this to the completely general scenario where you have this entangled probe systems available, but you don't do anything in between. And actually, there it turns out that you can still beat sort of these entangled probe systems, so the big entangled state, up to a certain number of particles. Say, okay, so one way to understand this, or one example what we looked at, was X and Y noise. So you have rank 2 noise. So ultimately this tells you, well, okay, there's no scaling advantage. You get a linear scaling at the end. So if you scale up the number of probes, eventually you will reach this standard quantum limit. So just something where your accuracy scales like 1 over square root of n. But on the other hand, that's an asymptotic statement. That's only telling you something about very large n. But what happens at intermediate stages? And then what we thought of, well, okay, some kinds of noise, the X noise, this can be cancelled. And now consider a scenario where X noise is dominant and there's only a small part of Y noise. Now, if you can sort of get rid of the whole X noise, and then the Y noise, well, okay, this Y is actually X and the Z. So there's sort of a part of noise in there which is parallel to your system. So this you cannot get rid of. But the large part of noise, the X noise, you can get rid of, and only the Y noise remains and becomes Z noise by doing this sort of error correction. And if you do something like this, using, and this is something I'll show you in a moment, you can do with just one auxiliary particle and one probe system. And if you do this, correct for X noise, transfer the Y noise to sort of logical Z noise, then actually with this method you can beat the performance of a very large entangled state. So by doing this intermediate control, doing this error correction on a small system, you can achieve the same or a better accuracy as with a parallel strategy. So that's what this simple sequential strategy is about. One probe system, one ancilla system, intermediate control. And you compare this to a big input state, large entangled state, which evolves and which you jointly measure. And jump over this. Well, of course, it depends on the asymmetry of the noise. But if the noise is very asymmetric, so if, say, the X noise or the Y noise is 10 to the minus 3 of the X noise, so if this is very asymmetric, then you outperform with this sequential strategy, the parallel one, really up to almost 400 particles. And I would say that's something quite useful because nobody has managed to really prepare a 400 particle GHZ state so far. I know that there are other entangled states being prepared, but they are not sort of as well suited as the GHZ states. But with the simple sequential strategy, you can actually beat this large system and just making the experiment with just 2 particles. And now let me tell you how this error correction actually works. And that's actually very simple. So the scenario you have to consider is now one sensing particle, one particle which is sensitive to the field, and which is also affected by the noise. And you have one auxiliary particle, which you have well under your control, and which is not interacting with the field, okay? You can play the same game in a little bit more complicated way if you don't have sort of a noiseless ancilla particle, if this thing is also coupled if it's also affected by noise, you can still do the same things, but the simplest scenario to understand how this works is by assuming, okay, I have one noiseless ancillar particle not coupling to the field. And in this case, you can use an encoding. Namely, you define state 0 logical, which is 0, 0, and the state 1 logical, which is 1, 1. So the 0, the first particle, it's the one which sees the field. The second is the one which doesn't see the field. So the evolution is really just a sigma z acting on the first particle. So only this term here, this 1, 1, this picks up a phase and this imprints the signal on the state. So this still works as it should. On the other hand, the noise is, in this case, an X noise. And it acts only on the first particle. And what an X noise does is just flip the spin. Now, if the first spin is flipped, well, this state, the 0, 0, goes to a 1, 0, and the 1, 1 goes to a 0, 1. And flipping a spin, well, that's a process which occurs only probabilistically. So either nothing happens, or the spin is flipped. That's what you write down when you write down the completely positive map corresponding to this X noise. So that's what I was doing here. So that's this 1 minus p is sort of the noise parameter, how strong the noise is. Now, so if an X error happens, actually this two-dimensional subspace where your signal is imprinted is transferred to another two-dimensional subspace. And that's exactly what happens in error, what you need in error correction, that your system subspace goes to some error syndrome subspace, which is orthogonal to the initial one. And now, since it's orthogonal, you can in principle just measure see in which of the two subspaces you are. And this way learn, okay, if I'm in this subspace, nothing happened, everything went nicely. And if I'm in this subspace, okay, some error happened. The only error which I considered and which I can correct now is that a spin flip occurred, and I can correct it by just undoing the spin flip. And in this case, you can really, without disturbing the signal, you can do the error correction. And that's in a nutshell what this error correction is about, as simple as this. And that's what you would do for this. It's the same protocol you would run in the sequential strategy I was just describing before. And if you look more closely on it, you realize that the Y noise actually transfers to a Z noise at the logical level, and the X noise is cancelled. Okay. Now there's one more trick I would like to share with you, because I think it's a nice one. It's similar. It's a similar setting as before. You have one sensing particle and you have auxiliary particles. Now, if you have this auxiliary particle or particles, this means in terms of energy levels, if you think of your Hamiltonian as Z only acting on the first particle, in terms of energy levels, well, your levels are highly degenerate. In this case, the 0, 0 and the 0, 1 is the upper energy, and the 1, 1, 1, 0 is the lower energy. And these two states, they are degenerate. They have the same energy, because only the Hamiltonian only acts on the first particle. But in principle, these levels are there, and in principle, you can manipulate them. Now, what you could do is now, again, during the evolution, manipulate your system a bit and say, switch the states 0, 1 and 1, 0, say at half time of your evolution. Now, this state 0, 1 will evolve forwards, and the 1, 0 evolves backwards for this other half. So the phase which is accumulated is 0 for these states, if you switch halfway in between these two states. So what this tells you is that actually you have generated an additional artificial energy level with your Hamiltonian. These two states, the 1, 1 and the 0, 0, they remain unchanged. But by switching between these two, you have generated an additional energy level. And actually you can, by choosing the time when you do this switching, you can actually choose the effective energy. In this case, we choose a half of the time, and that's why we got a 0 energy. If I would switch at a different time, I can sort of move this energy level downwards or upwards. So this is a tool which allows you to sort of generate effective energy levels in your in the evolution Hamiltonian. And that's actually something useful, not in the standard metrology scenario in the Fisher regime, but in the Bayesian regime. Bayesian regime is a metrology scenario where you have initial knowledge about your parameter. And you describe this knowledge by a probability distribution. Well, Fisher regime is a regime where you actually know almost exactly where you are. You know, okay, it must be this value, and you just want to know more digits. Then you can sort of describe everything with help of the Fisher information, and then it turns out that sort of only the energy gap tells you what's the accuracy which you can achieve. In the Bayesian scenario, where you say you have a flat distribution, for instance, for your field, you don't know at all how this field looks like. And actually, in this case, you can even have that your signal wraps around because the field is too strong. You cannot distinguish sort of several rotations from just a small evolution. There, these additional energy levels, they are very useful. They are really required in order to imprint the signal. And actually, the longer you let your system evolve, the longer your interrogation time is, the more levels you need. Because sort of these two levels, well, actually that's something we analyzed in this paper. So you start out optimal state just needing 2 levels, then for a longer time a third level is required, a fourth level is required, and these additional levels, you need them in order to distinguish your signal which you get from a wrapped signal which could also occur. So if the field was too strong, you want to sort of distinguish a situation where you just rotate it like this because you have a small field, or you rotate it like this because you had a larger field. And the longer you let your system evolve, the higher is the influence of these wrappings, and sort of the more intermediate levels are required. And we use this trick to have these more and more artificial levels in order to, on the one hand, really to find what's the optimal state. We showed how to get these additional levels, and actually we showed how to get them on the fly. So you don't really have to decide in the beginning how long you want to sense. But if you want to sense longer and longer and longer and learn more and more and more and more information, you can just sort of adjust dynamically the state and sort of introduce these intermediate artificial levels on the fly and sort of adjust your setting to the sensing time which is available. And at the end of the day, you do one measurement and then you get the maximal information out of it, and you really get the optimal scheme there. And of course, you need more and more auxiliary levels for this. And this is something I believe it's also quite a useful or powerful technique in order to manipulate also interaction Hamiltonians, because here we did it for a single qubit and a single sensing system. And I think the paper was called Optimal Sensing with a Single Qubit, because you just need one sensor and the rest are just auxiliary systems which help you to play these tricks and get these artificial levels. Now, at the level of Hamiltonian simulation, actually you could think of 2 qubits interacting with a ZZ interaction and having at these different sides auxiliary systems which don't interact at all. Now, by playing the same tricks and having these effective energy levels introduced, and just by sort of switching between states at some intermediate stage, you can actually mimic the evolution of two interacting D-level systems and get an arbitrary sort of diagonal D times D interaction Hamiltonian. And of course you can do more, because we know how to manipulate these D by D interactions, which are just in Z direction, to make them in XY direction, or to make them completely general, actually. And I think this could be a sort of a nice tool to design your digital quantum simulator with very simple basic interactions, namely just qubits, and then sort of blow them up to D-level system interactions. Now let me come to the last part, and I'm running out of time, I see, but I can maybe quickly give you the idea what this is about. Namely, this is about distributed metrology. So far, all I told you was about sensing some local field, some local quantity. Now what I have in mind is that your sensors are not all at the same position. They don't all of them see the same signal, but they are spatially distributed. You can either think of a really quantum network, so people are talking about this quantum internet now, and with the experimental progress, well, it might well be that we will have something like this in the near-term future, where you can think of having entangled states, not just in your single trap or locally here, but really distributed over larger distances. We even have entangled nodes already with several setups. But you can also think of this in a smaller scale, that you have particles in a trap which are not sitting at the same position. So if you think of an ion trap, well, an ion trap, the particles, they have a certain distance, or these NV centers in diamond, they are sort of located at different positions in space, and each of them sort of sees its own environment, it sees its own signal. And when you have a field which is not a constant, but when you have a field which is a gradient, the idea is how can you use these sort of spatially distributed systems in order to sense this non-local quantity. And there are one possible setting you can have in mind is that you have different sources. Say here you have a plate which gives you a constant field. Here you have some point sources with a quadratic thing. Here you have some dipole source with a 1 over r cube signal. And now here are your sensors, the red particles. And now you would like sort of to lock in to one of these signals. You're not interested in this constant field. You're not interested in this single point sources, but you are interested in this dipole thing. And you would like your sensors to only sense this dipole thing. And actually what we showed is that by having the appropriate number of sensors, namely just one sensor more than you have signals, you can actually choose the positions and the states. Actually, I should say the positions are given, and you choose just the states of your probes, entangled states of these probes, in such a way that you are insensitive to n-1 of these sources, only sensitive to one. And this has large consequences, namely because you choose your state that you are insensitive to these sources, you are also completely insensitive to noise of these sources. So it's not just that you don't see the signal of them, but you also don't see fluctuations of them. So the trick is really to say, well, I choose my state appropriately, I sort of construct my own decoherence-free subspace, as it's called, and it's much easier in this case, because now you have not only states which you can choose, but you also have positions which you can in principle vary. Or even if you let them fix, or if you arrange things on a chain or some square, that's also possible. That's not really a serious restriction. And then you can very generally show that if you just have enough of these sensors, you can always find two states such that they don't see all the other sources, and these two states are such that they see a signal from the remaining source. Yeah?
But you have to very well know all the other sources?
Well, in this case, okay, that's an artificial example, of course. In this case, you have to know where they are, but not the strengths of them. Okay? And of course, we did this analysis, also all of this we worked out for scalar fields, so still in this example of having some strengths of a magnetic field pointing in that direction, but now with some spatial correlation. So maybe, so that's really how this looks like. So you have a field where you have some spatial expansion function, and you are interested in the strengths of these different expansions. You can think, one example is to think of these different sources with different, at a different position. Another example would be you think of a Taylor series. So this would be the terms in the Taylor series. You have a constant part of your field, you have a linearly growing part of your field, you have a quadratic part, a cubic part, and so on. And that's also one expansion function. And then you are interested, say, just in the gradient. You are not interested in the constant part of the field, but just in the gradient, and you're not interested in the quadratic part. And And also in this case, you can really sort of lock into one of these coefficients, and maybe, so the easiest thing is for the gradient. So this state, so if you have now your sensors arranged on a line, now you would just use this sensor and this sensor, so just the outermost ones. And you prepare a state which looks like this. So these qubits here are in state 0, these are in state 1, or the other way around. That's this superposition state. Now this state, this is obviously not affected by a global field. Because a global field, well, you have the same numbers of zeros and ones, but just at different positions, so they pick up the same phase. So it's just a global phase, what you get from a constant field for this state. But in terms of the gradient, you pick up the highest possible signal. Because here you get the minus phase, here you get the plus phase. Because your ones are at a different position. So this is really an example of a state which is sensitive to the gradient and completely insensitive to a local field. And actually you can do this construction very generally, so for arbitrary expansion functions and so on and so forth. What is more, you can actually show that you need non-local entanglement, so entanglement between the sensors. In the sense that if you allow only for entanglement among a single sensor, in a noisy scenario, we cooked up an example where you actually get an exponential advantage by using this non-local entanglement, some sort of entangled state of all the distributed sensor particles, as compared to a situation where you only have entanglement among each individual sensors when you sort of view this as a local system. So there you can think of ion trap sitting here, another one in London, another one in Paris, and then you can have entanglement within your traps, but not among the traps. And there has been some discussion whether these situations are equivalent, or whether you can sort of use this local entanglement equally well than the non-local one. And actually there we showed, no, that's not the case. You really need this non-local entanglement, and actually you get an exponential improvement. I'm not sure, I won't tell you about how this is constructed. You can read this in the paper. Okay, and I think I better stop here and skip this bonus part on macroscopic quantum states. I would have prepared several slides on this, but I think I'm over time already, so I stop here. Thank you for your attention, and hope that at least you got some ideas of why or how this could be useful in quantum simulation as well. Can be what? Quantum can be classical?
Clustered as like a cluster of sensors, so you can...
But I would rather say it would be useful to cluster them. It's really useful to have this additional degree of freedom, the position, available, and make use of it. I think this is what I would learn from there. So, sorry, can you speak a bit louder? I can't.
What's the theoretical distribution limit for quantum sensing?
The theoretical what? The theoretical resolution.
Yeah.
Well, it's always this Heisenberg limit. It's this 1 over square root of n squared. So where the Fisher information is n squared. So really quadratically better than the standard quantum limit. That's the theoretical limit you can achieve. Mm-hmm.
So you, I think, understand that you consider always the GHD state as initial state when you apply to your...
No, I use this only as an example here. So all these bounds, what I showed you, it's really, there's no restriction on the initial state and no restriction on the measurement, because these are really channel bounds. They are just from the properties of the channel, you can bound the Fisher information which you can get independent of your initial state. So I only use the GHZ state sort of as an example to illustrate how things work, but of course all these general results, they are for arbitrary initial states. And I know that in some, there are, for some kinds of noise, the GHZ state is certainly not the optimal one. There are better states, there are the sticky states which perform better, and but all these bounds, they are not restricted to the initial state. And they are also not restricted to a particular measurement strategy.
So, of course, as you say, there are states which perform better, presence of noise, and others. So it will change from one state to the other. Because your results are also always asymptotic.
Yes,
right? So it means that you can have states up to 1,000 or 10,000 particles, scaling as Heisenberg, and when you go to 10 millions...
Well, actually, the results are not really asymptotic, because we... okay, on the one hand, you can use STBs, so you can sort of formulate things with linear programs, such that you can solve the finite size case efficiently. And on the other hand, for many interesting channels, we get explicit expressions for these prefactors, and so it's not really a scaling result anymore. It's really, we can tell you what's the bound, what's the precise bound for this kind of channel which you can achieve.
Yes, yeah. But if I understand correctly, I mean, these bounds are asymptotic. It means that you can have intermediate values of scales, which are these exponents larger than 1, subtraction noise, but only when n has become asymptotically large, these exponents depends on n, and so we go also to 1.
No, but wait, you have these two terms. So where is this? We had this alpha, so these two coefficients, some alpha, which was scaling linear in n, and the beta, where is this? It should be here. Right, this thing here. So that's a general expression, that's nothing asymptotic in here. Well, to make an asymptotic statement, you use the argument that, okay, if you can make this thing disappear, then you don't get a quadratic scaling. But you can keep this expression, compute bounds on these alpha and beta. This you can do for many interesting channels, amplitude damping, Pauli channels, whatsoever. And from there, you can also, for any finite n, derive a bound. And you know, then, okay, then it's still the question whether you can achieve it or not. But at least you can also find bounds also for this possible constant factor which you can get in between for a certain number of particles. And actually that's something what we did in this comparison of this sequential strategy with the parallel strategy. That we really ran these STPs in order to get for any finite n the optimal or at least a good bound for the performance. But then of course there's the question which states really allow you to achieve this.
So these are always, okay, I think we will discuss more about this. But the other question is, this is about uncorrelated noise, right?
Yes, yeah.
So if you have a correlated noise, then the situation changes.
Yes, yes.
You can have stuff completely equations-free subspace. You can have Heisenberg being
yes, yeah. Yeah, but these results, I have to say, these are for qubits only. All what I showed you are for qubits, but Pavel Sekatsky, whom I did this work with, and Rafael Demkovich-Jabransky, they generalized this later on to arbitrary systems. Also John Braskill, I think, did something there. And now they really have the complete picture under which conditions for any kind of Liouvillean, I think also dealing with this correlated noise, you are limited to the SQL scaling, and when you can still correct things and how you can do it.
So there is hope for metrology.
There is hope for metrology, yes.